Hello and welcome to our next unit in Math 10C. And this is going to be covering M4, so the fourth measurement outcome. And we're going to be looking at the idea of trigonometry. Okay, so if you have the notes, grab those somewhere, follow along. We'll go through some of these problems together. We'll give some time for you to try some. And we're going to look at some ideas about trigonometry, which is more of the study of triangles. So we've looked at triangles in the past. Right, talked a lot about Pythagorean theorem, the angles within triangles. We're going to explain the relationships between similar right triangles. And then the new topic here we're going to be looking at really is these primary trigonometric ratios. We're going to talk about finding the hypotenuse, giving a couple of other sides, right, solving some problems, using these ratios, as well as some of that foundation knowledge we already have, right, like Pythagorean theorem, and then possibly involving some indirect and direct measurement. So let's start with that new topic, that new idea of the trigonometric ratios. So when we have triangles, we can have things called similar triangles. Oops. And what that means, right, is there's the same ratio between corresponding sides, right? So I could have a triangle, right, that's long on the bottom, short on the side, and then of course the hypotenuse is the longest side. I could then have a similar triangle, right, that's still long on the bottom, short on the side, and my drawing is not very great, but assuming that these were the same ratios, right? If this had a length of 1, and this had a length of 2, right, then this one would have a length of, let's say, √5. If this was a similar triangle, say it was twice as big, right, this is 2, this is 4, and this would be 2 √5s, right? So everything here is equally related to each other, right? The bottom length is twice as big as the side, the hypotenuse is twice as long, right? These would be similar triangles. What that means is that they're also going to have the same angles, right? So we have this angle here, this small acute angle inside, and a 90 degrees. This is going to be the same angle, right? Even though the lines going out are longer, right? Angles don't care about the length of the lines, the length of those arms, right? All it cares about is the angle of rotation between them. So if everything is getting twice as large, right, that angle is going to stay the same, right? So that means that for every specific angle in a triangle, there must be a set ratio between sides. So what that means is if a triangle has a 45-degree angle, right, say, so something like this, we have 45 degrees. We know that with that angle, there's some way that these two sides, right, or all three sides are related, right? Some ratio between a pair of them. And these are what we call our trigonometric ratios. So trigonometry, right, the study of the properties of triangles, hence the tri part at the front. And specifically, we're going to be talking in this case about finding angles and side lengths within triangles. So we are going to look at three main ratios in this course. We're going to look at the tangent ratio, the sine ratio, and the cosine ratio. And these are what we call our primary trigonometric ratios. There is three more that you'll learn about in the future, but these are the main ones, right? These are the meat and potatoes, the bones of the angle ratios. Each of these is abbreviated. Tangent, we abbreviate to tan. Sine, we abbreviate to SIN. I'm still going to call it sine, it is not pronounced sin. And then cosine, we have cos. And you might actually be familiar with these because you might have seen these buttons on your calculators before. Right, and remember, when we're talking about a ratio, all of these are talking about ratios. It's the comparison of one thing to another. Generally, it's a fraction, right? We write it as the comparison of A to B, right? Slope is a ratio. It's comparing the change in Y to the change in X. Kilometers per hour, that's a ratio in your distance compared to the time. Here, those two things in our ratio are going to be the comparison of two sides, right? Two of those three sides of the triangle. We're only ever going to work with two sides at once, but that's why we have three ratios, because each of them describes a different pair of sides. It's really important to note here that this only works for right triangles, right, where we have that 90-degree angle in the corner. Right, so some right triangle, just like Pythagorean theorem, right, that only works for right triangles as well. Using these ratios, these primary ratios, only works for right triangles. If I have what I call an oblique triangle, right, where one of my angles is obtuse, bigger than 90 degrees, these rules that we're going to cover don't work. We have different rules to account for that we're going to cover in future courses. So we're focusing on right triangles only here. So in a right triangle, to be able to talk about what two sides each ratio is describing, we want to be able to name those sides. And the way we name those sides depends on what angle we're using in relation, right? The reference angle is what we call this. So here we use that theta, right? Theta. That's just our general variable for angles, right? We use x's and y's for points. You might see x's and y's here as well, but generally we're using theta to mean this is an unknown angle, right? And that being the amount of rotation from one arm to the other. How far does this open, right? What is the angle of rotation based off of this point in the corner here, this vertex of the triangle? And so when I'm looking from this angle, we are going to describe the sides with three main names. The first one is a name that we're probably familiar with already, and that's going to be the hypotenuse. Right? The hypotenuse, always the longest side of the triangle. To help us out, we can remember that it's always that length that's opposite our right angle. Right? The biggest angle in the triangle is going to create the longest side length. So we have our hypotenuse. That one we can label not necessarily based on our reference angle, but based on the triangle we see, right, and where our right angle is. We're then going to describe our other two angles our other two side lengths based off of that angle. We have the side that is opposite our angle, and we're going to call it exactly that, right? We have our angle in this corner. This side length, right, this red side length down the side here, is the only side length that isn't actually a part of this angle, right? It's not actually touching it, and it's opposite that angle. It's the side length opposite our reference angle. And then the last side, it is not opposite, but it is also not our hypotenuse. It's the side length that is touching, it's beside. It's what we're going to call the adjacent side length, right? And that's going to be the side length that's right attached to our angle, right? Adjacent means beside. But we want to make sure it's not the hypotenuse, right? Technically, the hypotenuse is also touching our angle, right? It's also beside our angle. But that one, because it's the longest side length, has a specific name. Now, again, this all depends on where our reference angle is. So if our reference angle, if instead I'm trying to know things about this angle up in the top instead, only the opposite and adjacent are going to switch. Right? The hypotenuse, the longest side of the triangle, hasn't moved. Just because we're looking at a different angle, the hypotenuse is still that longest side. However, now the side length that is opposite, right, furthest away from our reference angle is on the bottom. And the adjacent side length, right, the side length that's beside, that's attached to our angle, is now up on the side. Right? So making sure that you're labeling these sides, we're always going to use these three labels, always opposite, adjacent, and hypotenuse. Right? Those are the only three ways we can label the sides. We just have to really make sure which is which based off of that reference angle. So let's look at tangent first, right? The tangent ratio, which the value is usually expressed, like we said, as a fraction, right? Or we can turn that fraction into a decimal. And what that ratio means is it's comparing the lengths of the sides that are opposite and adjacent to that angle. So for some specific angle size, right, we can have an angle of 52 or an angle of 43, right? It's just comparing, it's telling us how big the opposite and the adjacent sides are compared to each other. So the tangent ratio looks like this. Tan of A, where A is an angle, right? You might also see it written like tan of theta. And we also sometimes shorten these op and adj, or O and A. And so what that's saying is that the tangent ratio, if I'm talking about the tangent ratio of an angle, it's telling me how big the opposite side is compared to the adjacent side. The tangent ratio doesn't tell us anything about how the hypotenuse compares, which is why we have two other ratios, right? Those will tell us some things about the hypotenuse. And a tangent, it's like a function, right? This is the tangent of an angle. It's not tangent times an angle, right? Tangent is not a thing without an angle within it, right? A lot of the time we actually see brackets around this angle to say that we're taking the tangent of an angle. So here we have our formula, right? Tangent of angle A is opposite over adjacent. So looking at this triangle, we have angle A here, right? We've labeled that vertex as angle A. When I'm talking about that tangent ratio, right, it's saying the opposite side, in this case, is going to be 6. Right? So a lot of the time, as soon as I see a triangle, I like to label the sides. I say, okay, here's my hypotenuse, right, across from that right angle. It's my longest side. I'm going to put an H there. This length of 6, this is going to be my opposite side because we're talking about angle A. If we were talking about angle B, things would be different. And then I'm going to call this side length A for adjacent, right, because that's the length that's adjacent to my angle that I'm referencing. So tangent of angle A, right, is talking about the opposite on top, so 6 over 2. And then what that reduces to is that the tangent of angle A is 3. What that means, right, what that's telling us, because it's a ratio, is that the opposite length is 3 times longer than the adjacent length. So that would hold true for any triangle where I have this specific angle A. And we're going to look in a little bit about finding out what angle that is. Okay? No two angles are going to give us the same ratio. So in any similar triangle, right, if I was to draw a triangle that was even bigger, let me try that again, because that bottom should be shorter. Right, I draw a triangle like this, where now the length of the bottom is 5. This is telling me, and this angle is the same, right? That's the key idea, is that this is only talking about the relationship between those two sides for angle A, which has a specific angle measurement that we just don't know yet. Right? It's saying that the opposite side is 3 times longer than the adjacent side, right? That ratio is 3, or 3 to 1, if we want to still look at it as a fraction. So if that adjacent length is 5, that opposite length should be 3 times as large. So these would be considered similar triangles. Right? Opposite side is 3 times longer than the adjacent here. So let's look at a couple of examples here. All right, so here we have triangle DEF, right? Named because it goes from angle D to angle E to angle F, or vertex D to E to F. Determine tan D, right? So determine the ratio of the sides that are opposite and adjacent from angle D, and determine the ratio of the angles that are, the lengths that are opposite and adjacent from angle F. So let's do tan of D first. So first thing, I'm going to write my formula. Opposite over adjacent. Right? From angle D, I want to make sure I'm labeling. Right? From this angle here, this side length 3 is that opposite length because it's on the opposite side of the triangle. And this side length 4 is the adjacent, right? Because this last length here between D and F, this has to be my hypotenuse because it's across from that right angle. So then I just make sure I substitute the right sides into the right points. So the tangent ratio of angle D is 3/4. And we generally leave this as a fraction, right? But if we want, we could convert that to a decimal, right? Tangent of an angle D is 0.75, right? All that means is that our opposite side is 0.75 times, right? Let me write that out. Opposite is 0.75 times our hypotenuse, or sorry, not hypotenuse, adjacent. Right? Our ratio less than 1, right, tells us our numerator is smaller. It tells us that my opposite side is shorter than my adjacent side. And all of this is talking specifically about an angle of measure D, whatever that happens to be. Right? We'll talk about finding that angle, but this is saying for a specific angle of this measurement, this is the set ratio that those sides are related by. Right? So angle F, we want to label that one separately. Right? Tangent of F, same ratio, right? Still the opposite and adjacent sides, but because we're talking about a new reference angle, right? Now length 4 is the opposite side, and length 3 is the adjacent side, because angle F is a different angle. So the tangent ratio of F is the opposite. It's 4/3. Right? Or if I wanted to write that as a decimal, that's 1.33 repeating, right? That's telling us that from an angle of size F, the opposite side should be longer than the adjacent side. Right here, the opposite side length is 1.33 times the adjacent side length. Right? It's longer. Another example, find the missing angles for the triangle GHJ. So, what does that mean, right? Well, it wants us to find angles G and angle J. And this is what we can use those tangent ratios for, right? It's just like any other equation we've ever done before. As long as I only have one unknown, I can solve for that unknown. So let's start with angle G. And we use this angle symbol. It looks like a less than symbol, but we try our best to make it flat along the bottom. Right? So angle G, again, I have my opposite side of 4 and my adjacent side of 5. Careful, sometimes these triangles flip around, but we can still tell, right, that the hypotenuse has to be, in this case, it's the one along the bottom, right, because it's the longest side and it's opposite that right angle. So for angle G, the tangent of angle G is that opposite, that 4, over that adjacent, that 5. Right? And to solve an equation, I want to isolate my unknown. I need to isolate G. And to isolate a variable, we have to undo, right, do the opposite operation of everything that's around it. Well, here, the operation that's around it is a tangent, right? This is tan of G. I can't divide by tan because tan isn't a thing, right? That's like you saying I'm dividing by multiply, right? It's not a value. It's just an operation. So I need to figure out what the opposite operation is and do that to both sides, right? Like I always do. So I'm going to pull up a calculator here, and this is just a general scientific calculator. This is the Desmos one, but the operation is going to be the same idea on whatever calculator you're using. Right, we see here, if you look on the left-hand side, I have my sine, my cos, and my tangent buttons. We're not going to write it like that because that's sine of cos of tan. That's a lot of mess. But we want the opposite. So we want to hit the second button. Right? Or in this case, I'm hitting function. And you're going to see the sine -1, the cosine -1, and the tangent -1 to the power of -1. And what that means is the inverse of sine or cosine or tangent. And so that's what we want. That's the opposite. That's the operation that undoes a sine, cosine, or tangent operation. Usually on most graphing calculators, you can find these right above the sine, cosine, and tangent buttons in the second operation. So if you hit the second button and then sine, cosine, or tangent, it usually gives you these options. So what I want to do is I want to essentially untangent the left side. So if I take the inverse tangent of the left side, all right, it's kind of like it unlocks this tangent. It's like the key. It opens this gate. These two both disappear, and I'm just left with g. Right? Just like how if I had off to the side, say I had something like 2x equals 5, right? That x is being multiplied by 2. If I divide by 2, right, those two operations undo each other. This tangent and this tangent inverse undo each other. But I can't just change one half of the equation and say it's still equal. So I have to do the same thing to the other side. So what that looks like here is I have to take the inverse tangent of this ratio. So I'm taking the inverse tangent of 4/5. Right? This is me telling the calculator, I know the ratio is 4/5. Work backwards for me and tell me what angle, right, angle G in this case, actually gives me a relationship like that. So I'm going to open up my calculator again. I'm going to select this tangent inverse button, and then I'm just going to type in my fraction. All right, we had 4/5. Again, I'm just going to do 4 divided by 5. Yours might not split into 2 lines like this, but that's okay. And it tells us our answer, right? 38.6598, blah, 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 blah. That means that any angle of this size is going to have the opposite and adjacent sides related in this specific ratio, right? 4 times the opposite divided by 5 times the adjacent, right? The adjacent is slightly bigger. So that gives us our solution for G. That tells us that angle G is, and we'll round to maybe a couple decimal places, let's call it 6.66 or even 0.7. Let's say 38.7 degrees. Right, so it's a fairly acute angle, it's small, it's 38.7 degrees. Now to find J, I could do the same thing, right? I could find the opposite, I could find the adjacent, I could inverse tangent that. But we know a few things about triangles, right? We know that, let's go through this angle J. We know that a triangle has 3 angles that total to 180 degrees, right? That's what makes it a triangle. If the angles inside were more than 180 degrees, there would be a gap, right? None of the corners would meet. If it was less than 180 degrees, it wouldn't work, right? Triangle angles have to total to 180 degrees. And just like in every other equation, if I know everything but one unknown, I can solve for that unknown. Here, I know angle G, right? I know it's 38.7 degrees. I also know angle H, right? Because I know that this has to be a right angle. I know that this has a measure of 90 degrees. So I know that angles G and H and J have to total to 180 degrees. And I know 2 of those 3 angles. Angle G is 38.7. Angle H is 90. And then angle J is our unknown. If I do some algebra, right, I bring everything to the other side, I subtract 180 by 90, right, I bring 90 to the other side, and I subtract that 38.7, that's going to tell me angle J. So going back to our calculator, ideally we've left this value up here, right, so that I can go 180 minus, and I'm going to select answer, right? So it's not taking the rounded value. We're getting as close to the exact value of J, minus 90. Tells me I'm left with 51.3 degrees that I can put towards angle J. So 51.3 degrees. And so we have all of our angles now. We have angle J, we have angle G, and we knew angle H, right? We found the missing angles. One thing to note is we're talking about all of these angles in degrees, right? That's our unit of measurement for talking about angle measurements. But your calculator might not be in degree mode, right? There's another unit we're going to look at, right? It's like measuring in centimeters versus inches. It's still talking about angles of rotation, but there's another unit called radians, and this is actually what your calculator defaults to. So if you want to make sure you're in degree mode, if you're on a graphing calculator, this is the instructions for the TI-84, or 83, 84, right? All of those. You want to hit mode. It's the button right near the top, right beside your second button. And then you want to make sure you go down, highlight degree, and hit enter. If you're on a Casio graphing calculator, you want to go shift and then menu. That's going to take you to setup. And then you're going to go down to where it says angle here at the bottom. Sorry, it's a little small. And then you're going to use your F keys, right, those buttons along the top, to decide the one that says degree. And that's going to be the F1 button. And then you're in the right mode, right? If you're getting different answers, if you try to go through this example and you're getting different values, usually smaller numbers or sometimes even negative numbers, that means your calculator is likely in the wrong mode. If you're on a regular scientific calculator, there's a lot of different ways. This one just has a flip, right? A switch flip. You probably have a mode button, or it might even say degree. Look for the words mode. And if you're stuck on that, send me an email and we can help you through that. So let's look at how this can be used, some problem solving with this. So here we have the latitude of Fort Smith is approximately 60 degrees. The position of a solar panel should be close to its latitude. So that's hoping, right, meaning that hopefully the solar panel is propped up to an angle of 60 degrees, right? But we don't know that yet. Is this the best design for a house in Fort Smith, right? We want to make sure that the sun is coming down and hitting this solar panel at an angle of 60 degrees. So let's check. Right, we have our triangle, and if we want, we can draw it out again, out of context, just to help us out. Right, we're looking for angle, let's call it L for latitude. And we know we have 9 foot of height in that roof, and 12 feet in width for half of the roof, right? Because we're working with right triangles, we only want to look at half of this, right? We want to make sure it has that nice 90-degree angle in the middle. So let's check. Okay. I want to say that angle L, right? We're going to use the tangent ratio because, again, if I label my sides first, right, I have 9 as my opposite. I have 12 as my adjacent, and I have the actual roof length as my hypotenuse because it's opposite that right angle. So tangent of angle L, right, the ratio of the sides compared to angle L is opposite side over adjacent side, right? Make sure this isn't getting flipped upside down. It has to be opposite on top, adjacent on the bottom. Now I know those values. Right? The opposite had a length of 9. The adjacent had a length of 12. Because I'm isolating my unknown, right, I need to isolate L. L is trapped inside this tangent, so we do the inverse. Right? That's what gets us L by itself. But to be able to do one thing to the left side, I have to do the same thing to the right side. If it helps, right, if your calculator doesn't do fractions very well, we can figure out what 9 over 12 is first as a decimal. And then I can take the tangent function of that. But again, make sure you're using something like an answer button If it's a number that you would be rounding, try and keep the entire exact value. Trigonometry is going to do a lot of crazy things to your numbers. So the more you round, the farther off your true answer will be. So if at all possible, try and use, if you have an answer button on your calculator, or keep at least, I would say, if you're in the middle of a question, keep at least 3 decimal places. Right? If you need to use that value again, the more you've rounded it, the more it will affect things. So let me find out, right, from our calculator that this angle is actually 36.8, or if we round to the nearest degree, angle L is 37 degrees. And we're looking for 60 degrees. So clearly, we could say, no, this design is not best. Right? Because our angle is much less than 60 degrees. Right? We're not getting quite the right amount of sunshine if we place our solar panel at this angle for Fort Smith. One last example. So a 10-foot ladder leans against the side of a building with its base 4 feet from the wall. So a 10-foot ladder leans against the side of a building with its base 4 feet from the wall. What angle to the nearest degree does the ladder make with the ground? All right, so here we have a brick wall. We'll draw our ladder in. All right, it's propped up against there. And it's telling us that its base is 4 feet from the wall. So the length from the base of the wall to the base of the ladder is 4 feet. And the ladder is 10 feet long. So this green line, our hypotenuse in this case, is 10 feet. What angle to the nearest degree does the ladder make with the ground? So we're looking for this angle down here. Right, let's call that angle theta. Well, if I want to find out this angle, right, I need to know the opposite side and the adjacent side. But right now I have a problem. Because when I look here, the opposite side, right, is how far up our wall the ladder hits. And we don't actually have that information yet. Right? We know how long the ladder is. We know the hypotenuse. But remember that the tangent ratio doesn't actually say anything about the hypotenuse. It doesn't take the hypotenuse into consideration. So how can I find the third side when I know 3 sides of a triangle? Well, we already know that a squared plus b squared equals c squared. Or in this case, if we want to change that up, right, opposite squared and adjacent squared has to give us our hypotenuse squared. Right, we can find that third side. Like we can find O, right, the height that the ladder hits up the wall, to help us figure out then what the tangent ratio looks like. So let's plug in the values we know. We don't know the opposite side, right? That's what we're trying to find. But we do know the adjacent side. We know that the ladder, right, the adjacent side to theta, is 4 feet. Oops. So we'll put plus 4 squared equals, and we also know the hypotenuse, right? Across from that right angle, the wall and the ground, right, is making that right angle. My hypotenuse is 10 feet. So piece by piece, right, I'm going to isolate O. Let's square all those values first. O squared, and O might not have been the best variable to use because this really looks like a 0, plus 16 equals 100. If I bring the 16 to the other side, right, I'm subtracting. O squared is 84. And then the last thing I'm going to do, I need to square root both sides because I need to find out the length of just O, not O squared. Right, to undo that square, I square root. And I'll just pull up my calculator here. We'll take the square root of 84. And that gives me 9.16. Right, again, we want to keep a few decimal places if we're not done a problem. I'm going to call this 9.165. Actually, I'm even going to call this root 84 for now. Right? We can round. We can call it 9.165. right? 9.165 or 9.17, but we don't want to round too far because we're not done yet. So the opposite length is root 84, or if we'd rather work in decimals, let's call it 9.165, right? Just so we're really not altering that all too much. Now we can go ahead, now we can use our tangent ratio. So tangent of theta equals the opposite, which is that 9.165 or that root 84 over the adjacent. The adjacent was that 4 feet. Right, and this one is also in feet. Make sure we have some units there. Right. Again, has nothing to do with the hypotenuse, so we're not including that 10 anywhere. Trying to find the angle, so I inverse tan both sides. I'm taking the inverse tangent of root 84 divided by 4. Alright, so I might find that value first. That might be easiest for me. If I figure out root 84 divided by 4, careful that 4 is not underneath the radical. Or like we did before, I could do root 84 first and then divide that by 4. Oops. Answer divided by 4, right? If you have the possibility to use that answer feature, please do. Keeps all those decimals for you. And then I need to take the inverse tangent. So I find my tan inverse, where I hit second tan if I'm on a graphing calculator, of that same answer, right? That 2.29. That's telling us the tangent ratio, right? That 2.29 tells us that the opposite side is 2.29 times bigger than the adjacent side. And the angle that makes that ratio true looks like it's 66.4. So theta equals 66.4 degrees. And I'm sorry, I'm not sure what's going on with these lines. But lucky for us, that's where we're going to finish off this video. So when we come back, we're going to start to look at, great, what happens when I have the angle? How can I find one of those unknown sides for that tangent ratio? So if you have any questions, let me know, and I'll get back to you as soon as I can. Stop by your tutorials, stop in by Focus, and keep working on some of that practice.